All right, so in this video, we're going to introduce the idea of a triple integral now. And you can see that the example on the screen, you've got the triple integral instead of the double. This t now is not going to just be a region t as much as it is now going to be a closed solid region t. So now we're dealing with a solid instead of just a planar region. So closed solid region. And then we have this dv out here as opposed to a dA. The dA was some combination of dx, dy, dy, dx. Here, since we have the triple integral, we'll need some combination of dz, dy, dx, or something like that. Now, in this particular problem, you'll notice once we get it set up to evaluate it, we're just going to do the same thing as we did earlier with double integrals, except now we have another iteration. So to get it set up, we'll want to take a look at this closed solid region that they're giving us. And remember that the order that we set up this dv, which would be some combination of, again, dz, dy, dx, would need to come out in such a way that we ended with our constants. All right, so knowing that we're going to need to end with our constants tells us that at minimum we know we need to end with y. We're going to end with y, so that's going to be a pi over 6 and a pi over 2 there. So pi over 6, pi over 2. And that's again telling us we're going to end with y. Now, as far as the other two go, some of this, a lot of this actually, depends on what's going to be easiest to integrate with respect to. Now, I've found that in setting this up, that the easiest way to integrate is actually going to be in the order of dz, dx, dy. And so if that's the route we choose to go, then the first one would be z, and z would be bounded between 0 and xy, and the x there would be in the middle between y and pi over 2. So again, ending with y is definitely something we have to do because of the constants. These two, you get a little bit of an option depending on the ease of integration. So let's actually go ahead and run through this. Now, our first one will be this integral right here, so it'll be with respect to z. So as I integrate this with respect to z, the 1 over y is a constant, which means that when I continue on, let me just go ahead and copy these down real quick. So when I continue on, that's going to be a y sine z over y. All right, so again, the 1 over y, there's the constant. The z is what I'm integrating with respect to. That's where the sine came from. So in theory, that is a u sub, but one that we've done so many times by now that I think it's apparent the y would just come out in front. So then we would evaluate this guy. And again, this would be at z equals 0 and z equals xy with our dx, dy off to the side. So let me copy this down again. And so when I evaluate, when I plug in the xy for z, that's going to give me a y sine x. And then when I plug in the 0 for z, that's just going to wipe the whole thing out. So I think we're ready to move on to the dx now, followed by the dy. So now I'm focusing in on this iteration here. And in doing so, my pi over 6 and pi over 2 are still there. Integrating this guy with respect to x is going to give us a negative y cosine x being evaluated from x equals y to x equals pi over 2. And we still have our dy there. So now, as I evaluate this, the pi over 2 being plugged in here for x is going to zero this guy out. Then we'll have minus, I'll plug that in. So the double negative goes away, creating just a y cosine y. So we have a y cosine y dy that's going to be left. And we have a pi over 6 and a pi over 2. So we continue on here. Now, this is just a basic Calc 2 integral at this point. I say Calc 2 because of the technique we need. This is going to be an integration by parts. Even though it's a single variable, it's still an integration by parts. So we've got our u, we've got our dv, our du, and our v. And if you remember the whole I late, this is the order in which we select the u. So we don't have any inverses, we don't have any logs. The algebra would be the y. And then the rest of it would be the dv. So that's going to be cosine y dy. So if our u is equal to y, then our du is going to be dy. And then over here, if I integrate both of those, our v is going to be sine of y. So the formula, if you'll remember from Calc 2, was uv minus the integral of v du. And I always try to set mine up the same way, so it's just a matter of recognition. uv minus the integral of v du. So we've got now y sine y minus the integral of sine y dy. And y sine y followed up by now plus cosine y from this guy right here. And that all still needs to be then evaluated from y equals pi over 6 to y equals pi over 2. So if you go ahead and plug in the pi over 2 in for this, you're going to get a pi over 2 times 1. And then the pi over 2 being plugged in here gives us the 0, so plus 0. And then minus our pi over 6 being plugged in here, which would be a pi over 6 times 1/2. And then the cosine here at pi over 6 would be a root 3 over 2. And so in cleaning this up, it actually turns out to be 5 pi over 12 minus root 3 over 2 for the final answer. So the big takeaway here isn't as much of the process, because you can see it's very clearly the same thing as we would have for double integrals with just another iteration. But the big takeaway is getting it set up. And then, of course, this particular example, I wanted to remind you guys of the integration by parts technique.